Swayam Prabha. Digital India. Educated India.
Dear students, we are back with the lecture series of course material on Transportation Engineering 2. From the previous lectures, we have started with the taxiways once we have completed about the runways. Now, taxiways, as we have discussed, is another important aspect or a component of any airport which provides the connectivity and access between the runway strip and the terminal building or the apron related to terminal building. So, in that sense it is one of the component which creates its effect on the airport capacity, because the way by which the aircrafts can be turned around and can be taken away from the runway strip as fast as possible will create its effect on the total capacity which can be handled by any of the airport. In continuation of the same, in today's lecture we will be discussing about exit taxiway, a specific type of a taxiway which is used for providing that type of movement from a runway strip to the terminal apron. So, in that case, in this particular lecture we will be taking up exit taxiway, the turnaround taxiway and taxi lane. These are the three major components or the three specific type of components of the taxiway which we can discuss. We will be starting with exit taxiway. Exit taxiway, the function of this exit taxiway is basically to minimize the runway occupancy time of landed aircrafts. As we have discussed previously, that the taxiway, the main function of a taxiway is to provide an access between runway strip and terminal building. So, in that sense it provides the pathway for those aircrafts which have landed on the runway strip and now proceeding towards the terminal building, or those aircrafts which are being there on the terminal building apron and now they are proceeding towards the runway strip for takeoff. In both the conditions, as we have seen and we have discussed previously, is that if there are more than one taxiway, then we try to provide the unidirectional movement, and that sense only here we are discussing the exit taxiway, where at number of locations we provide an opportunity from where any landing aircraft can come out of the runway strip, so that the runway is not remained occupied by that aircraft and can be utilized for another operation, maybe landing or takeoff. So, that is why the main function is here is, or the objective here is to minimize the runway occupancy time. The average runway occupancy time of any landed aircraft, it is frequently determine the capacity of the runway system, and not only the runway system, but it also determines the overall capacity of any airport. So, that is obvious, because if any aircraft is taking more time at the time of landing before coming towards the terminal building apron, then no other operation can take place on that runway strip. So, it means we are reducing the overall capacity of not only the traffic handling capacity of the runway strip, but also of the airport. So, that is why this is average runway occupancy time is an important factor, and it is to be measured and optimized in the sense that it is minimum as far as possible. Now, when the angle of turnoff is of the order of 30 degrees, then the term high speed exit or rapid exit taxi lane is used. That depends on at what particular angle the exit taxiway is being provided. If this is being provided at an angle of around 30 degrees, then we say that this turn will be taken up at a higher speed, and that is why this is a high speed exit or a rapid exit taxiway. Now, there are certain typical exit taxiways. Now, this is one of the diagram which tries to define that how the taxiway is being exit taxiway is being provided. Now, here this is the runway strip, and on this runway strip an aircraft will be landing from this direction, that is from left hand side, and it will be moving towards the right hand side, and there is a taxiway which is a parallel lane, a parallel pathway, a paved area being provided with respect to this runway strip. So, the aircraft has to be taken from this runway strip to this main taxiway, so that this particular runway can be utilized for some other purpose. So, in that sense a connectivity is being provided between this taxiway and this runway strip, and this is what is this type of a connectivity, and this connectivity is known as exit taxiway. That is, it is trying to provide an exit from the runway strip and then it comes towards the taxiway. So, in that sense the number of design features have been shown here. This is the runway strip which is in natural condition, whatever is the width being defined, like here we have the width being defined here is 45 meters, which is for the higher category of an airport, and at this level the angle of turning from this side, this is 35 degrees, whereas accordingly from this side it is 180 minus 35 degrees. And here the two curves are being provided. There is one curve which is known as the entrance curve. The length of this entrance curve is L1 with a radius R1, and the degree with which this turn is taking place is defined by D1. Whereas there is a circular central curve which is provided in this location, and this is having a length L2 with a radius R2 and a deflection angle as D2. So, there is a relationship between this deflection angle D2 and another deflection angle D1, and that is we can calculate them, as we will be seeing when we will be computing the values for all these different design parameters. Now, in this particular location where there is a turn at this point, as we have seen previously, or we will be looking in today's lecture too, that if there is any plane which is taking a turn, then there are different ways by which it can be done. Either the nose may be moving along the center line of the pathway, or there is another method in which the pilot uses the judgmental approach and tries to negotiate that curve, wherein the nose gear will be going away from the center line, but at the same time the inner gear of the main gear on the wing will remain within the area which is away from the inner side of the pavement. So, in that sense there is always a possibility, depending on the type of the method, that we are moving away from the edge of the pavement, and therefore, this paved area is to be provided, which is known as fillet. So, there will be extension of this paved area towards the inner side, and that particular area will be termed as the fillet area. Now, here the width of the exit taxiway and the width of the main taxiway is also being shown, which is 22.5 meters, again being provided for a higher category of airports, and a fillet is to be provided on this side as well as on this side. So, these two areas are also for fillets, and then there is a side distance which is being provided. This is the side distance being provided from the center of this curve, central curve, towards the point of intersection of this center line of the exit taxiway with the main taxiway. At the same time, there is another design parameter, which is the distance between the center line of the exit this main taxiway and the center line of the runway strip, which is termed as the separation distance between the runway and the taxiway. So, that separation distance needs to be calculated. So, these are some design features which have their significance in the design of any exit taxiway, and we will be looking at all these design features and the computation of these design parameters. Now, we first of all look at the conditions which defines the location of any exit taxiway. There are certain factors on which this may be depending, and the factors are like for large and small aircraft, we may require different initial exit speeds. That is one particular condition that is also known to us. because it all depends upon the type of the propulsion power which is being provided on any of the aircraft. And if the aircraft is big enough, then the power will also be more, and therefore the speed with which it will be landing will be more as compared to the smaller aircrafts. Therefore, we have to look at what is the exit speed of different type of aircrafts which will be using that airport and the exit taxiway. Then there is a touchdown distance at which the aircraft will be touching the pavement surface when it is coming along the flight path and descending on the runway strip. So, this touchdown distance from the runway threshold and the runway occupancy time, these both are needed to be determined, and they will be dependent on the approach speed with which it is crossing the threshold and the touchdown speed. So, these are the two values which are the another important factor or parameter which will be defining that for how much time period an aircraft is going to remain on the runway strip. If the aircraft is crossing the runway threshold with a smaller speed, lesser speed, then it will be touching down a little early or may touch down at the pre-specified point, but then it will be coming towards the exit taxiway location with a smaller speed, and therefore, there is a more of occupancy time in this case. Whereas an aircraft coming with a higher speed at touchdown location also, it is having a higher speed, then it will be moving with the same that big higher speed, and therefore, the chances of occupancy time will remain lesser. So, that is another design parameter or factor which will create its effect on occupancy time. Then the another factor is the rate of deceleration here, and this rate of deceleration is also dependent on certain parameters like the pavement surface condition. And within this pavement surface condition, it may be a possibility that this is in the wet condition or it is in the dry condition. So, on both these conditions, then it is having a different coefficient of friction which creates this effect at the time the aircraft is trying to deaccelerate, or the pavement surface will be providing some resistance in the opposite direction. Obviously, in the dry condition, the coefficient of friction will be more as compared to the wet condition. So, in that case, in the case of a dry condition, the rate of deceleration will be more, and therefore, the aircraft can be brought to a desired smaller speed earlier as compared to a wet condition. And another factor is that this rate of deceleration should be such that the passengers should not feel jerks, or there should not be any discomfort to them at the time when the aircraft is trying to reduce its speed. So, these are the two factors which creates this effect, or which governs the value of rate of deceleration. As far as ICAO is concerned, then ICAO has recommended a deceleration rate of 1.25 meter per square second. So, that is the rate which can be used if it is not being specified otherwise by any of the other airport authority governing the air navigation in any of the country. Further, there is another factor like we have to look at the size of the airport, and if there is a large airport, then there may be as many as 3 angled exit taxiways for each landing direction. In addition, this will be there with respect to the several 90-degree exit taxiways. So, it depends, means if it is going to be used by a large number of aircrafts and the frequency of their landing is much more, then in that case we require a number of taxiways, and these taxiways, the exit taxiways being provided, there may be the angled taxiways provided and the 90-degree taxiways being provided. So, that is a combination of these needs to be provided. What it says is that other than the 90 degrees exit taxiways which have been provided, there should be 3 angled taxiways for each landing direction. Now, the 3 angled taxiways will be spaced at different distances along the runway strip, so that they can take care of different type of aircrafts which will be landing with with respect to the propulsive power with them, and the efficiency or the fastness or rapidity with which those aircrafts can be taken away from the runway strip towards the main taxiways. While designing these exit taxiways or locating these exit taxiways, the another factor which is also taken into consideration is the pilot judgment. At times the pilot judges by themselves that they have reached a speed by which they can now take a turn and can move towards the taxiway. So, after what particular time interval that is being felt, on the basis of that we also the exit taxiway can be located along the runway strip. Now, once we are looking and once we are talking about the location of any exit taxiway along the runway strip, then one thing which can be looked upon is the optimum location of that exit taxiway. And in this case, the fundamental principle remains is that it should be having the minimum runway occupancy time, and this is what we have just discussed before also when we started over this lecture. What it wants to say is that as we have discussed before, that the runway should be occupied for as less a time as possible per landing. So, that remains the fundamental principle. So, we have to locate it such way that the delays are not there. Further, it is dependent upon the acceptance rate of the runway with the taxiway system and the arrival rate of aircraft. These are the some other factors which governs whether we are having the optimum location or not. What it tries to say is that there are two things which are happening. One is that the runway system is having the arrival rate of the aircrafts. On the basis of the number of aircrafts which are going to land on that airport, there will be a specified arrival rate at which these aircrafts will be coming. And then there is another rate which is known as the acceptance rate of that runway. Acceptance rate of that runway means that whether the runway is in a position to take an aircraft which is approaching this airport, and this is obviously is going to be dependent on the overall capacity of the airport and the provision of the taxiways by which the runway becomes empty. And when there is no other aircraft on the runway strip, then the next aircraft can utilize that for landing. So, therefore, the acceptance rate of the runway strip and the arrival rate of the aircraft on the airport, these are the two things which will be governing the occupancy time and the optimum location. The runway occupancy time then in that case can be treated as consisting of two parts. One is that from the threshold to the touchdown, and another is from touchdown to exit. That is the two main constituents of computing the runway occupancy time. As we have discussed that an aircraft, if this is the runway strip and then the aircraft is landing from this side. So, if this is the end of runway strip, so that is the threshold, and if the aircraft is crossing this threshold and is touching the runway strip somewhere here. So, how much time it has taken so as to touch this runway, this particular touchdown point. So, that is one of the time period, and then once it has touched here and there is an exit taxiway being provided here. So, how much time it takes to reach from this touchdown point to the exit taxiway, so that it can take a turn around and come out of the runway strip. So, in that sense, the total occupancy of this runway strip will be constituting of two components. One is the time being taken between threshold and touchdown point, and another is the time being taken from the touchdown point to the exit condition. So, here it is going to be controlled by the speed with which the aircraft is crossing the threshold, and here it is going to be controlled by the touchdown speed and the speed of the exit. So, these are the two speeds which will be there. So, here it is speed from threshold to the touchdown. So, we will be taking three speeds into consideration in that sense. So, if we want to compute the distance from the runway threshold to the exit speed condition, then it will be given by the value as E is equals to, that is the distance for the exit condition or distance for the exit taxiway will be equals to STD, where STD is the aircraft touchdown distance, that is once it has crossed the threshold and touches the pavement at some point, then within that particular those two points, whatever is the distance being covered, that is STD plus it is VTD square minus VE square divided by 2A. So, here this VTD is the aircraft touchdown speed, the speed at which it is touching down the pavement surface, and V is the aircraft exit speed at which it is coming out of the runway strip. And this A, this is the average runway deceleration rate from touchdown to the exit speed. So, on the basis of this value, so if this is known to us depending on the speed between this is the aircraft touchdown distance, that is the distance being known most of the time, because this is defined that for this type of an aircraft it is going to touch at this position based on its flight path and based on its speed at which it is crossing the threshold. So, that is this known generally, and therefore, this value can be taken directly. Otherwise, this can also be computed on the basis of the speed of an aircraft at the threshold point and the speed of the aircraft at the touchdown point. So, with respect to those two speed, we can compute the value. Now, this occupancy time which we have been discussing from the runway threshold to exit speed consists of the flight time from the runway threshold to touchdown point, because here now if we are interested to find out the time in the just previously what we have seen is the distance which is being moved, and that distance probably is the overall distance which is required for locating the exit taxiway. So, after reaching that particular distance, then exit taxiway can be provided at that location, and which will be probably the optimum location for that aircraft. Now, the another thing which we are interested in is to minimize the occupancy time, and in that sense it is going to be consisting of like the flight time from the runway threshold to the touchdown point. That is the one aspect as we have discussed. Another thing is the time required for the nose gear to make contact with the pavement surface, because when it touches down the pavement, the aircraft, then at that point it is the main gears which are provided below the wings. So, first of all those main gears touch the ground, and once they have touched the ground, then after that slowly the nose gear touches the ground. So, there is some gap between this whole movement, and this is usually 3 seconds. So, it means we have to take this 3 seconds into consideration, and then there is a time to reach the exit speed from the touchdown speed. So, there is a change from touchdown speed to the exit speed, where the exit speed is lower than the touchdown speed, and that is happening after the nose gear has contacted the pavement surface and the brakes have started being applied. So, in that particular condition, then we are looking at this changeover. And another is the time required for the aircraft to turn off on the exit taxiway and clear the runway. Approximately this is taken as 10 seconds. So, we have two constant values, 3 seconds and 10 seconds, and then in between those we have certain time periods which needs to be computed on the basis of the speeds. Therefore, this runway time from runway threshold to exit speed in seconds, can be given by this occupancy time is equals to STD divided by half of VTH plus VTD, and this whole is being added to 3 seconds, that is the time which is being taken by the nose gear to touch the pavement surface, plus the change in the speed from touchdown to the exit, that is VTD minus VE divided by A, that is the deceleration rate, because the brakes are being applied so as to reach this value of VE, plus 10 seconds being given so that the aircraft can take a turn around turn off and can come towards the taxiway. So, that is the overall time period which is to be considered, and this time is the occupancy time of any runway strip, and this needs to be minimized. Now, here we are looking at the concept of this optimum location concept, which in the starting when we were discussing about the various factors, we have come across that there are two different types of rates which govern that how we can find out the optimum location. Here those rates are like the average occupancy rate, acceptance rate, and the arrival rate. So, this arrival rate is the rate at which the aircrafts are reaching any airport, and this acceptance rate is related to the runway strip with which it is being able to accept the aircraft for landing. Now, so far the arrival rate and acceptance rate both are same. We will get a curve something like this. So, this is the curve, this is a straight line profile which shows and which is moving at maybe the 45 degrees. So, this shows that whatever is the rate the aircraft is being accepted in this system. But then after some time, after some particular rate, the condition will come wherein the arrival rate will remain, but the runway strip is not in a position, or the overall airport is not in a position to accept further aircrafts. It means now at this particular position, though if both the things would have remained same, then this should have been the curve, but here now because that is not the condition. So, the arrival rate remains the same, that is it is coming with the same rate still as like this, but the acceptance has reached the saturation point, and therefore, there is no further possibility of accepting any other aircraft on this airport, and therefore, it becomes constant like this. So, at this point where it becomes constant, where still the arrival rate is increasing, that then this point is known as the balancing point, that is the aircraft this airport is in a position to accept the number of aircraft which are going to be defined by this point of intersection or this point of changeover in the value of acceptance rate, where the acceptance rate becomes constant. So, this is the number, this is going to define the overall capacity of any airport in this particular way. Now, here when the arrival rate is still there, that means there are still the aircrafts which are coming on, but they cannot be accepted. So, therefore, there is going to be a difference between the two values, that is the acceptance rate and the arrival rate, and this value is known as wave off, means these are the number of aircrafts which needs to be turned away from the airport, or probably they have to be told to keep circling at the top of the airport, so that as soon as they have airport has the space or can accommodate any more aircraft, then they will allow one of them to land, and that is how it will go on. So, in this case if the runway is capable of accepting all the aircrafts up to a certain arrival rate, that is if these two rates are same, then this particular point at which this relationship becomes valid, or up to which this relationship becomes valid, is known as the balancing point. That is already we have seen in the figure. Now, as the arrival rate further increases, the acceptance rate begins to fall, and it reaches a point of saturation. So, after this point of saturation, then whatever aircrafts are coming after that, as I have told you, they needed to be waved off, and therefore, the waved off is the condition when the aircraft arriving at an airport does not complete landing, because the runway is occupied at the time the landing is to be made. So, that is the situation on any of the airport, and this happens at number of times if there are meteorological problems associated at that airport. Now, this exit location of the taxiway is to be oriented such that it yields the highest possible rate of acceptance, and if we can orient in this form, then this condition is known as optimum location. So, that is how we can locate the optimum location of any exit taxiway. Now, within this exit taxiway, now FAA recommends that the following optimum distances of the taxiway from runway threshold can be taken up depending on what type of aircraft is going to use any airport. Like in this case, if there is a twin engine propeller driven transport aircraft with a large twin engine general aviation or aircraft, these are the two type of the aircrafts. If they are there, then as per FAA, the optimum distance of the exit taxiway from runway threshold is 750 meters. Whereas, if there is a 4 engine propeller driven transport aircraft or a turboprop or a twin engine turbojet, then in that case it requires 1200 meters as a distance. Whereas, if it is a large turbojet transport aircraft, then it requires 1800 meters. So, as the size of the aircraft, as the propulsive power of the aircraft is increasing, keep on increasing, that this distance also keep on increasing. So, in this case we look at that there are certain corrections which needs to be provided for the optimum distance of any exit taxiway, and one such correction is for the altitude and temperature, and this is given by this equation SSC, that is the correction for the distance S is equals to S plus m multiplied with the 76 divided by p, and it is further multiplied with 4.92 plus 1.8 times of t, and it is here divided by 5.19, and then the whole value from whole of the value m is subtracted, that is minus m. Now, whatever these abbreviations which have been used here, we look at those abbreviations, and they are: S is the distance from the runway end to the exit taxiway on a standard day in meters, m is 150 for turbojet, and for others it is 195. P is the standard air pressure in centimeters of mercury. T is the average temperature of the hottest month. Now, this assumes that there is no wind condition, means there is no wind blowing. If there is a headwind of 16 kilometers per hour, then it is being observed experimentally, then it may reduce the distance by 13.5%. So, the effect of wind, if it is there, then it can be taken in this form. Now, some of the common taxiway intersection designs and details have been shown in this figure, where this is a T sort of a junction. We have the taxiway being provided here, and this is the exit taxiway being provided. So, we have a curve from this side as well as from this side, and this is the width of the taxiway, whereas this WT is the width of the exit taxiway, and here after this is a straight portion, and then after that the flaring starts, it goes up to a length L, whereas here also up to a length L. Then we have a point of rotation that is, and this defines the radius r. So, similarly, this is a condition where there is a crossing being provided between a taxiway and an exit taxiway, and it is taking the traffic further. So, these are the two, or the two taxiways are crossing each other. So, similarly, all the figures have been shown here. Here it is in the form of a L taxiway, that is it is a sort of a turning for the end of say the runway strip, and that is how we can see the two type difference. Now, another thing which is related to the exit taxiway is its geometric values, and these geometric values are defined by the airplane design group. And here what we see is that the width ranges from 7.5 meters for a design group category 1 to 30 meters for a design group category of 6, whereas the edge safety margin again in meters varies from 1.5 meters at a minimum to 6 meters at the maximum. Then there is a center line radius which varies from 22.5 meters for a category 1 to 51 meters for the category that is 6. Length of the fillet also varies, and initially it is 15 meters, and then for category 3 it is 45 meters, and for rest of the bigger categories it is 75 meters. Then further there are some more things like the fillet radius, and this fillet radius can be computed on the basis of the type of the steering, which is like judgmental oversteering, and in this case if it is a symmetrical condition it varies from 18.75 meters to 33 meters, again for the airplane design group ranging from category 1 to category 6. Then if there is widening, then if there is a one side widening, in this case it will be 18.75 meters to 30 meters. So there is some variation in these values, a small difference. And the fillet radius in the case of center line tracking, that is the nose of the aircraft is moving along the center line, then in that case the value varies from 18 meters to 25.5 meters. Now we come to the methods of traversing that we have seen, of course, these methods of traversing before also. Now we are looking at the same thing here, that is the cockpit is following the center line of the turn, that is this nose is moving along the center line. So what we have seen is that it moves like this, but while doing this way there is a slight tilting of the aircrafts towards the inner side, and what is being observed that in this case this wheel path will go away from the inner edge of the pavement surface. That is why the fillet needs to be provided which with a full strength, so that it can take the load of the aircraft which is moving in this form. So this is one method which is also recommended by ICAO, whereas there is another method like the judgmental oversteering method. In this judgmental oversteering method, this nose is not going along the center line of the strip, whereas it goes a little away, so that this inner wing of the main gear, it remains well within the edge of the pavement surface, and therefore we require a smaller size of the fillet in this case if this type of method is being used. But the nose is going a little away and it will come back to the position after a certain, once it is with this curve is being negotiated. So here there is no tilting of the aircraft, and the aircraft remains within the same central position. So that is the another type of condition. So in these cases we have to determine that by what particular value the extra widening needs to be provided or the fillet area needs to be provided. So what we have seen is that the path of nose gear and main gears are different, and then at the time of traversing a curve, and these are therefore there is a method of traversing wherein the some extra widening is required on the inner side of the intersection. So in that case here we have this another figure where we are trying to show the same thing. This is the nose gear and this is the center line, this is going along the center line, and these are the main gear threads, and these are the body gear threads being provided behind those one. So what we can see is that they are taking their own different turning conditions. So this is the normal condition, like they are going straight. This is a steering in this direction at an angle of some value that is known as caster angle, and this caster angle can be at the maximum 70 degrees. Now the turning is going with respect to here. So this is the point of turning. So therefore this is the radius at which this turning is taking place, and this is the pavement edge within which this remains. And here again in this particular side, body gears that they are taking a turn in this direction and they will be coming towards this direction. So, here this angle can be at the maximum 13 degrees. So, the distance from this point to this axis on which these two wing gears are, that is the wheel base which will be available at this condition. So, we will be using this wheel base so as to determine that at in what particular position the curve will be negotiated by the nose gear and by the main gear. So, there is a graphical method of doing that, and in that graphical method, first of all we draw the path of the nose gear, which say being defined as M1, N1, N8, N for nose gear, M for main gear. Then what we do is that we set our compass to represent the wheel base, which we have seen in the previous figure. And once we have got this distance, then we mark the initial position of the wheel base on any guiding line and say that is M1, N1. So, if whatever is the path which we have from this point M1, we take this much distance and just make a point on this curve. So, that will be M1, N1 position. Then once we have done this, what we do is that we come a little lower than the value M1, say to position M2, which is lying on the same curve, and then we mark another location N2. So, that is a M2, N2 location. So, likewise we keep on going, and again we place a compass at a short distance of M2 and mark N3, and we keep on repeating this. And once we do this way, then we will be getting another locations of the points, that is M1, M2, M3, etc., and this particular line path will be known as the path of the main gear. So, that is how we can find out that how the paths will be differentiating. Here we can see in this diagram that this is M1, this is N1, and then this is N8. So, this is the guiding line, or this is the line along which the nose wheel will be moving. So, this is how it is going to happen. Now, the wheel base is equivalent to M1, N1. So, we have taken some point M1 here, and with the help of the compass we have located the point N1. Now, once we have done this, then we come short of this M1 and we take a point M2 and cut it some way, so that we have another point N2 at some distance here. So, that is lying on this straight, and this is how we keep on going, and we keep on marking the points on this side. So, the distance from M8 to N8 should remain equivalent to the distance as of the wheel base. So, whatever the path we are getting in this form, this path is the midpoint of the main gear path. Now, we come to the design of the taxiway, and there are certain principles which governs that design. In the case of a small aircraft, the turn of exit speed is taken as 65 kilometers per hour at an exit taxiway angle of 45 degrees to the runway center line. Whereas, in the case of large aircrafts, this turn of speed at the exit time is taken as 95 kilometers per hour, where the angle of intersection is taken as 30 degrees. So, that is the rapid condition of the exit taxiway. This is a diagram which shows the components which we have to design, that is this is the runway. From this point it starts moving away from the runway strip. So, this is the initial curve, that is L1 with the radius R1. Then there is another central curve which is having a length L2 and radius R2, and it goes in this form, and then after this again it will become a straight line. Now, another thing is that for a smooth and comfortable turn, a circular curve of large radius is provided, so that an aircraft can negotiate it without significant speed reduction. That is the thing which we have seen as another curve, that is central curve with the length L2 and radius R2, and the radius of this one can be found out by a formula V square divided by 125F, where V is the speed on turning in kilometers per hour, that is the speed with which it is taking a turn or exiting, and F is the friction factor. Usually this friction factor is taken as 0.13. And then this R2 value can also be computed by using the Horenzef formula, which is 0.388 W square, and this is divided by half of T minus S, where this W is the wheel base length of the aircraft in meters, and T is the width of taxiway pavement in meters, and S is the distance between center of main gear and edge of taxiway pavement, again in meters. Now, there is a slightly widening entrance which is provided, which is gradually tapering to the normal width of the taxiway, and this is preferred, and the fillets are also used for widening. In the case of this compound curve is provided, then it reduces the wear on the nose gear, and it is relatively easier to lay in the field. In this case, the value of radius R1, that is being shown like in the previous diagram with the length L1 here, it is defined on the basis of the exit speed with which the aircraft is coming out of the runway, and if it is 65 kilometers per hour, then this R1 is taken as 517 meters. If it is 80 kilometers per hour, then it is taken as 731 meters, and if it is 95 kilometers per hour, then this value of R1 is taken as 941 meters. Now, the length of entrance curve is estimated as L1, and this is V cube divided by 45.5 C multiplied with R2. Now, here the V is the aircraft exit speed, R2 is as computed previously, that is the radius of the central curve, and C is the factor which is normally taken as 0.39. Now, the deflection angle for the entrance curve, that is for the initial curve of the compound curve, is D1, and this can be computed as given by this formula like 180 into L1 divided by pi into R1, and we know the R1, we know L1, so we can compute the value of D1. Now, the length of the central curve is computed by the formula pi into R2 into D2 divided by 180. So, these are all on the basis of the properties of the circular curve only. Now, here D2 is the deflection angle of the central curve, and this can be computed by taking the coster angle or the turning angle and subtracting D1 from this value. R2 is the radius of central curve. Then there is a side distance which needs to be provided, and this side distance defines the stopping distance basically, because this is the point up to which the aircraft can be stopped without any accident taking place. So, therefore, this governs the comfortable deceleration rate with which the aircraft is deaccelerating and leaving the runway strip. And this can be computed by the equation as shown here, that is as d is equals to v square divided by 25.50 multiplied with d, where this d is the average rate of deceleration, and if it is not known, then it is generally taken as 1 meter per square second. In the case of ICAO, that is being defined as 1.25 meter per square second. Now, in the case of smaller airports, the air traffic may not be sufficient to justify the construction of parallel runways. So, in those cases, then what we provide is the turnaround taxiway, where the taxiing is done on the runway itself, and a turnaround is provided at the end of the runway strip. So, that is the condition which is termed as the turnaround taxiway. These also serves the purpose of holding apron, means this is a type of the apron which is to be provided, which we will be discussing in the coming lectures. But what we can understand here is that it provides the condition where an aircraft can be stored for some time period if there is an emergency. So, that is what a holding apron is. Therefore, it also helps in the way that it can be used as holding apron. Now, here in this figure, the same thing is being depicted, where this is the center line of the taxiway, or this may be the runway strip itself, and then here we are providing the turning of the aircraft, and the aircraft comes up to this location, it takes a turn like this, comes back in this one, and then goes in this direction and gets exited. So, that is the type of the turnaround condition is being provided, and this distance remains variable depending on the type of the aircraft which are going to use this type of a facility. Most of the time these aircrafts are of a smaller size, because these facilities are provided on generally on the smaller airports. In future, if this is to be extended and parallel taxiway needs to be provided, then this can be extended in this direction as being shown by dotted lines. The another type of feature is the taxi lane. In the case of taxi lane, this is a portion of the aircraft parking area here being used for access between the taxiways and the aircraft parking position. So, that is how it is defined. So, as we understand that in the case of the terminal buildings, the aircrafts will be standing just in front of the terminal buildings, and if the similar sort of a condition is there, or there is a parking of those aircrafts at the other side, then in between these two type of parkings there will be some pathway, and that particular pathway is termed as taxi lane, which provides the connectivity, which provides the area through which the aircrafts can move and can access either the parking area or can access the terminal building, or may move towards the taxiways. Now, as far as ICAO is concerned, it defines this taxi lane as an aircraft stand taxi lane as a portion of the apron intended to provide access to only the aircraft stands. That is how it defines it. It simply speaks about the aircraft stands to which the aircraft will be moving, and whatever portion of the taxi lane is used for that purpose is taxi lane. So, in this photograph, a taxi lane is being shown. Here we can see that there is a terminal building on this side along with the terminal building on this side, and these are the gate positions being provided where the aircrafts can stand and the passengers can board the aircraft. Similar is the condition on this side. We can see the aircraft standing on this position and on this position. And then here we have the runway strip at the farthest condition, where we can see the takeoff aircraft and the landing aircraft simultaneously come in doing on the two different runway strips. And then this is the taxiway being provided. Here is another taxiway being provided. So, there are the parallel taxiways on which different aircrafts are moving. So, in this case, there is a connectivity being provided from these taxiways to this parking area, that is this apron as well as this terminal apron. So, we have the terminal apron on these two sides, and the aircraft is moving in between these two areas, and this particular area is known as taxi lane. Now, here is another figure where the concepts have been shown, that this is the runway strip and these are the two parallel taxiways being provided. And as we can see that there is a unidirectional movement on these taxiways, the aircraft moving towards the left on this one and towards the right on this one, so as to increase the safety as well as efficiency of the airport. And then from this particular taxiway, then there is a connectivity being provided to this terminal building on which the aircrafts are being the aircraft stand is being provided on this side, and this side for boarding of the passengers, similarly on this side. So, whatever the space is being left in the center, so that this aircraft can come to this direction and move towards the taxiway, or from this side it can come to this direction and can take a position on the stand. So, this area is the taxi lane. So, some of the details have also been shown, that what is the distances which needs to be provided here. This is another close up of the same condition, where we have the taxi lanes, two taxi lanes being provided with their center lines like this. So, in this case, if we have to design this taxi lane, so what we need to consider is that the minimum taxiway center line to center line to taxi lane center line separation is provided as 1.2 times the wingspan of the most demanding aircraft plus 3 meters. So, that is how we can compute the value between the two center lines. Then the separation between the taxi lane center line and the parallel taxi lane center line or a fixed or movable object in the terminal area is predicted on a wing tip clearance of approximately 1/2 that required for an apparent taxiway. So, this is another thing which is to be considered, and this is here we have to look at the distance which is being provided in the case of apparent taxiway, and the clearance which is provided between the taxi lane center line and the fixed removable object in the terminal area is half of that distance. And this value is dependent on the low taxiing speed in the area, the taxiing is precise or not, and the special guidance techniques and devices which are provided for doing the taxiing. Further, a minimum separation between the taxiway center lines of 1.1 times the wingspan of the most demanding aircraft plus 3 meters can be provided, though the desirable, as we have seen previously, is 1.2 times the wingspan plus 3 meters. The separation between a taxi lane center line and the fixed or movable object is of 0.6 times the wingspan of the most demanding aircraft plus 3 meters. So, everything is going to be governed by the wingspan of the most demanding aircraft or the biggest aircraft which is going to generally utilize that lane or that airport. Therefore, when dual parallel taxi lanes are provided in any of the terminal apron area, then the taxi lane object free area becomes 2.3 times the wingspan of most demanding aircraft plus 9 meters. So, that is the overall size of any of the dual parallel taxi lanes will become as being shown previously. So, 3 meters, this 9 meters is taken on the 3 meters on the two sides plus 3 meters in the center of the two aircrafts. So, that is the clearance being provided as we have seen previously. So, this is how we can design any of the taxi lane. So, in today's lecture what we have seen is that how we can design any of the exit taxi lanes so that we can improve upon the airport capacity in terms of reducing the occupancy time of any aircraft on the runway strip. And we have also seen the various design factors which creates its influence on finding the value of the occupancy time, or as well as finding the distance at which the optimally the exit taxiway needs to be located. Along with the taxiway, exit taxiway, we have also seen their design principles and the design parameters in their computation, and then we have also looked at two specific type of conditions which are termed as the taxi turnaround taxiway and the taxi lane. So, we will stopping at this point, and will continuing with our discussions on airport engineering in the coming lectures. Till then, goodbye and thank you to all of you.